Hello class, my name's Asher and this is an instructional video on how to do problem number 25.71 in our Mastering Physics homework. Now, before we begin, let's read through the question. The figure shows a thin rod with charge Q that has been bent into a semicircle of radius r. Find an expression for the electric potential at the center. Give your answer in terms of Q, R, and appropriate constants. Okay. Hopefully editing Asher has successfully superimposed that question right there onto the whiteboard so that you can still see it while I'm doing this problem. Now, I'm going to start off by drawing our picture on the whiteboard and labeling our values on it so that we can see that too. So, here's our semicircle of charges. There are a bunch of charges there. I'll kind of like write plus signs here to make that clear. There we go. And then we have our point, which is in the center, right there. And here is r, the distance to any part of the semicircle from the center. There we go. And the whole semicircle is made up of a total charge q. That's all of the semicircle. And for the sake of clarity, I'm also going to introduce another variable L, and that will be the entire length of the semicircle. So I'm not sure how to signify that. Maybe I'll just like put some arrows here. That's the whole length of the semicircle. There we go. Alright, now we also have a couple of known equations that I will write down, and one of which is our equation for electric potential, which is V equals K times Q all over R, like that. And we also know the equation for linear charge density, which is what we need here, because while our charges are lined up in a semicircle, they still all fall upon one line, so therefore the linear charge density is the equation that we still want. And so that equation is lambda, so lambda equals Q all over L. L is that length of the charges. Now we also know that we can split this semicircle up into infinitesimally small pieces, which I can call dl. So dl can be represented by, right there, that will be dl, right in those lines. Here, I'm going to make those clearer. Right there. And in those pieces are infinitesimally small increments of q, which I can call dq. So, to recap, this is a very small portion of L, and inside that very small portion of L are very small portions of Q, right there. Now, to show this in our electric potential equation, we can differentiate both sides to get dV. dV equals K dQ all over R. Well, in many problems, we have seen that r, which is the distance away from the charge, changes. In this case, it is a constant. And that's because right here is our point, and as we can see, r is going to be exactly the same no matter where on the semicircle we measure, because it's a semicircle, and this is the center of the semicircle. So the radius of a circle never changes. This will come up later because we don't integrate or differentiate constants like we do variables, so that helps us out. Now, in order to successfully complete this equation, we need to get rid of our dq and instead have this in terms of length. So in order to do this, we must manipulate our linear charge density equation. So let's rearrange things a bit so that it reads q equals lambda times L. We can now differentiate both sides so that it equates to dq instead of just q. So dq equals lambda times dl. Alright, now if you notice, we have an equation for lambda up here. Lambda equals q over L. So we can plug those two values into the value lambda right here so that our equation reads dq equals q over L times dl. Now that we have this value, we can substitute everything on the right side of the equation here into our electric potential equation to cancel out dq. So let's do that. That'll be dV equals K times Q over L times dl all over R. And I wrote it like that just to get dl on its own right here to make it easier later on. Okay, I have erased some of the stuff right here so that we can have more room. I have written our work to alter the linear charge density equation up here, so you can still look at that. So right now, this is what we have. We can alter that slightly by moving L to the bottom right here, just to make it look nicer. So that's going to look like this. dV equals K times Q all over L times R dl. Just like that. Okay, so now that we have everything substituted in, we can integrate it to see what our final equation looks like. And in most cases, we would need to write which points we are integrating between, but because in this case every one of our values are constants and don't change, being that the distance from the center to any point on the semicircle is always exactly the same, we don't need to worry about that. So I'll write out our equation with our integral sign. So we have the integral of dv, it looks like this black marker is dying, that's fine, and that equals, and then we can move all of these outside of the integral sign because all four of these are constants. They represent constants. R is a constant because it doesn't change throughout the circle. Q is a constant because that's the total charge of the circle. K is always a constant because that's Coulomb's constant right there. And L is a constant because that's the length of the semicircle. So we can move these outside of the integral. This is really dying. All right, just like that. And then times the integral of dl. Okay, I wrote everything out a bit smaller so that we have more room down here again. So using this, we can therefore see that V equals KQ over LR times L, just like that, which we can then cancel out both of those L's so that V equals KQ over R. Now, you may notice that this equation looks exactly like the one right here, and you're absolutely correct. The reason why you can find the electric potential at this point right here so easily is because, as I mentioned before, every single letter here represents a constant instead of a variable, like we have seen it represent before. So in most cases, the R value will change depending on where on the line of charges you are looking. However, because our point is the exact center of a semicircle, R never changes either, which means that every single one of our variables are constants. Therefore, if we know the total charge of a semicircle of charges, just like this, then we can actually calculate it exactly like we can calculate the electric potential of a point charge, just by our electric potential equals Coulomb's constant times total charge over our distance between the point and anywhere on our semicircle of charges. So, V equals KQ over R is our answer. Hopefully this helped you, and have a wonderful day. Good luck solving those physics problems.